Hello students, welcome to EPG Pathshala. I am Dr. Javed Ali from Department of Pharmaceutics, Faculty of Pharmacy, Jamia Hamdard, New Delhi. And today here we are going to discuss about a module on cosmetic chemistry under paper cosmetics. The objective of the today's module is talking about liquid, surface tension and viscosity, solid with respect to amorphous and the crystalline nature, the symmetry of crystals, physical properties of crystals, polymorphisms, physical properties of material potentially used in cosmetic necessities like acids, bases, buffering agents, topical agents, protectives, antimicrobials, and astringent, and the chemistry of emulsions in cosmetic formulation. Cosmetic chemistry, when we talk of, is the nature of formulation is solely based upon excipients chemistry. A good formulation scientist should have good knowledge of this chemistry of every ingredient used for the formulation, and he can also anticipate the interaction, the incompatibilities which are occurring with the ingredients within. The latest edition of the Cosmetic Toiletries and Fragrance Association, referred to as CTFA, dictionary lists more than 10,000 raw materials. Every year, hundreds of new ingredients are added to this list, and compatibility, stability, appearance, applicability all depend upon the chemistry of the excipients of the raw materials. Now, coming to liquids, surface tension. Surface tension is defined as an energy or a work required to increase the surface area of a liquid due to its intermolecular forces. It is the elastic tendency of a fluid surface which makes it acquire the least surface area possible, and soap is added to water to reduce its surface tension. The substances which are used for reducing surface tensions are known as surfactant, and a very common example is that of sodium lauryl sulfate. It is known in the cosmetic industry, surfactants are the foundation of nearly all formulations and cosmetic science in general. Coming to how the surfactant works in an emulsion, when surfactants are put into solutions, the molecules of surfactants have a tendency to line up in a specific way depending on the solution composition, the concentration of the surfactant, and the temperature. In aqueous solution with extremely low surfactant concentrations, the molecules tend to bounce around randomly without forming structures. But at the CMC, which is the critical micelle concentration, they arrange themselves in spherical structures which are termed as micelles. On the outer layer of the spheres are the hydrophilic part of the surfactant molecule, and on the inner layer are lipophilic parts. Increased surfactant concentration give more complicated structures, resulting in hexagonal cylinders, lamellar planes, and liquid crystals. Today, surfactants are used to produce stable and elegant cosmetic formulations. Surfactants are used for cleansing, emulsification, solubilization, conditioning, and special effects like antimicrobial effects. The surface tensions, as discussed, is basically determined by various instrumentation like stalmometer, Wilmey plate method, ring detachment methods, which is also known as dew noise tensiometers. These are the instruments which are used for determination of surface tension. These instruments measure surface tension at laboratory scale. Coming to the another fundamental property of the liquid, which is viscosity, and the viscosity of a fluid is measurement of how sticky it is. Water has fairly low viscosity. Shampoo or syrups, they have higher viscosity than water. It also depends on temperature. Flowing fluids through pipes produces a resistive force due to its viscosity. This resistance can be basically be thought of a frictional force acting between parts of the fluid that are traveling at different speeds. Fluids very close to the pipe walls travel more slowly than the fluid in the very center of the pipe. It is a liquid property and described as viscosity as a measure of resistance to gradual deformation by shear or tensile stress. For liquid, it has direct relation with thickness. For example, honey has a much higher viscosity than water. A fluid that has no resistance to shear stress is known as an ideal or inviscid fluid. Zero viscosity is observed only at very low temperatures in superfluids. The physical basis of viscosity. The viscosity is a measure of the ease with which molecules move past one another. We have already talked about this. And it depends on the attractive force between the molecules. It depends on whether there are structural features which may cause neighboring molecule to become entangled. Viscosity decreases with increasing temperature, and the increasing kinetic energy overcome the attractive forces, and molecules can more easily move past each other. The different types of viscosity are described, namely as dynamic, which is also known as shear viscosity, kinematic viscosity, and bulk viscosity. So the measurement of viscosity, how long a liquid takes to flow out of a pipette under the force of gravity, how fast an object like steel ball sinks through the liquid under gravitational force, are the basis of measurement of viscosity. The dynamic shear viscosity expresses its resistance to shearing flows between adjacent layers which move parallel to each other with varying speed. It is defined through the idealized situation known as coite flow, where a fluid layer is strapped between two horizontal layer plates, one fixed and one moving horizontally at constant speed. This fluid has to be homogeneous in layer and in different shear stresses. Dynamic viscosity is the tangential force per unit area required to move one horizontal plane with respect to another plane at a unit velocity when maintaining a unit distance apart in the fluid. The kinematic viscosity is a ratio of absolute or dynamic viscosity to density, a quantity in which no force is involved. Kinematic viscosity can be obtained by dividing the absolute viscosity of a fluid with the fluid mass density. The third type is the bulk viscosity, which is while a compressible fluid is compressed or expanded without any shear, it exhibits internal frictions that resist flow. The force which are related to rate of compression or expansion by a factor are called the volume viscosity, bulk viscosity, or second viscosity. The bulk viscosity is important only when the fluid is being rapidly compressed or expanded, and such compressed or expanded bulk viscosity explains the loss of energy in those waves as described by Stokes' law of sound attenuation. Now coming to solids, it is characterized by the structural rigidity and resistance to change in shape or volume. As we all know that for majority of cosmetic products, solids content and types play an important role in stability of product. Therefore, for example, amorphous solid powder is more soluble than crystalline powder. It reflects that more amount of amorphous powder will be dissolved, solubilized in small volume of liquid to enhance the appearance. And hence, the solids in formulations are classified as amorphous and crystalline solids. When the atoms are tightly bound to each other in solid in a regular geometric lattice, it is crystalline solid, or irregular, it is being termed as amorphous solids. Coming to polymorphism, which is the ability of a solid material to exhibit more than one form or crystal structure. Now, the we have seen the solids are of mainly two types, amorphous and crystalline solids, and polymorphism is shown by the crystalline solid. Solid content and types play a major role in stability of the product, and as we have seen, amorphous solid powders are more soluble than crystalline powder. It reflects more amount of amorphous powder which will be dissolved or solubilized in small volume of liquid to enhance the appearance as such. Polymorphism can potentially be found in any crystalline material including polymers, maybe minerals, metals, and it is related to allotropy, which refers to chemical elements. The complete morphology of a material is described by polymorphism and other variables such as crystal habit, amorphous fraction, or crystallographic defects. Polymorphism is relevant to the fields of pharmaceuticals, cosmeceuticals, agrochemicals, pigments, dyestuffs, foods, and explosives. Two another terms are also used in polymorphism, which are anisotropy and monotropy. Anisotropy, in some cases, one polymorphic form can change into another at a definite temperature when the two forms have a common vapor pressure. This temperature is known as transition temperature. One form is stable above this temperature and the other form is below it. When the change of one form to the other at the transition temperature is reversible, the phenomenon is called anisotropy, and polymeric forms anisotropes. For example, rhombic sulfur, that is alpha sulfur, on heating changes to monoclinic sulfur, that is beta sulfur, at 95.6 degrees Celsius, which is a transition temperature. Also, monoclinic sulfur on cooling again changes to rhombic sulfur at 95.6 degrees Celsius. Monotropy, it occurs when one form is stable and another is metastable. The metastable changes to the stable form at all temperatures and changes are not reversible. Thus, there is no transition temperature and the vapor pressure are never equal. This type of polymorphism is exhibited by phosphorus. A number of methods have been employed for characterizing polymorphs in pharmaceutical solids. Polarizing optical microscopy and thermomicroscopy have proven to be useful tools. Thermal analysis procedures such as DSC, that is differential scanning calorimetry, and thermogravimetric analysis, that is TGA, can be used to obtain additional information including phase changes and to deduce whether each isolated form is solvate or anhydrate. These thermal methodologies are employed to distinguish between an anisotropic and monotropic system. For an anisotropic system, the relative stability of a pair of solid forms inverts at some transition temperature beneath the melting point, while a single form is always more stable beneath the melting point in a monotropic system. The solid-state characteristics of drug excipients are known to potentially exert significant influence on solubility parameters. Polymers of a drug substance can have different apparent aqueous solubility and dissolution rate, and when such differences are sufficiently large, then it is often difficult to formulate stable cosmetic products using different polymorphs. Solubility, as a defined temperature and pressure, is a saturation concentration of the dissolved drug in equilibrium with the solid content. Aqueous solubility of drugs is traditionally determined using the equilibrium solubility method that involved suspending an excess amount of solid content in selected aqueous medium. The equilibrium solubility method may not be suitable to determine the solubility of a metastable form, since a metastable form may convert to stable form during the experimentation. An amorphous solid is a liquid that does not flow. Its atomic structure is disordered like that of a liquid, but it is rigid and hold its shape like a solid. Amorphous materials include silica gel and multitude of other materials of different origin, such as soft glasses. They are often found on various kitchen table, mayonnaise, chocolate mousse, or ketchup, or in our bathrooms in the form of various gels or beauty creams. These soft glasses are actually capable of flowing if forced, but can be spread with a knife just like liquid honey. When the solubility of a metastable form of a drug substance cannot be determined by the equilibrium method, the intrinsic dissolution method may be useful to deduce the relative solubility of metastable forms. Use of the intrinsic dissolution method assumes that the intrinsic dissolution rate is proportional to the solubility, the proportionality constant being the transport rate constant, which is constant under the same hydrodynamic condition in a transport controlled dissolution process. Polymorphic differences and transformation that result in different apparent solubility and dissolution rates are generally detected by dissolution testing. This test provides a suitable means to identify and control the quality of a product from stability perspective. When solubility and dissolution rates of the relevant polymorphs forms are sufficiently high, regulatory concerns with respect to bioavailability and stability are minimum. The BCS, that is the Biopharmaceutical Classification System criteria of high solubility and rapid dissolution should be considered in regulatory decisions. Although the chemistry of amorphous and crystalline drugs will be the same, the rate and ease with which reactions occur will differ as it will be accelerated in case of amorphous. This makes the amorphous solid less stable than the corresponding crystalline phase. For example, lactose is usually avoided in formulating amine-containing drug because of the possibility of the well-known Maillard reaction between amines and sugars. This reaction is responsible for the non-enzymatic browning of some food. Study of this reaction using the amine containing drug like metoclopramide and lactose as a model system indicate that high reaction rates were found for amorphous samples of either the drug or lactose. Now, coming to the physical properties of materials potentially used in cosmetics, and these properties include dielectric constant, refractive index, molar refraction, optical activity, and adsorption. Coming to dielectric constant, the dielectric constant is a ratio of the permittivity of a substance to the permittivity of free space. It is expression of the content to which a material concentrates electric flux and is the electric equivalent of relative magnetic permeability. As the dielectric constant increases, the electric flux density increases. If all other factors remain unchanged, material solvents with high dielectric constants are useful in the manufacturing of formulations which are to be used in deep effects. High permeability will be requirement of non-staining cosmeceuticals. Thus, the materials having high dielectric constant but optimum should be preferred for cosmetic preparation. Now coming to refractive index, the refractive index or index of refraction of a material is a dimensionless number that describes how light propagates through that medium. When light travels at an angle between two materials, it bends according to their refractive indices. In order to reflect, the light must be on the wider side of the critical angle. Current consumer trends favor clear products in the cosmetic market. To meet this requirement, chemists have developed two ways to make clear emulsions, either by microemulsion and by refractive index matching. The former has been widely explored, leading to many microemulsions conditioning products in the market, and in contrast, the latter has not been widely explored because the physical principle is not well explained and there has been no practical methodology to follow to realize many different applications. The exploration of refractive index matching in formulation of cosmetic by a practical method has been used, which leads to development of many unique cosmetic formulation. Refractive index matching enables formulation scientists to make many unique formulas that cannot be achieved by other methods. Refractive index matching should become a common technique for formulation scientists. Cosmetic scientists are interested in knowing how to calculate the refractive index of a solution and how to design a formula with the refractive index of each ingredient in solution. It turns out that if one mixes several miscible ingredients together to form a clear homogeneous liquid phase, the refractive index of the mixture can be calculated from each individual component's refractive index in the composition. Thus, it is an important parameter which gives a good elegance of product, not only emulsion but also to other preparations. Now coming to molar refractions, which is also being termed as molar refractivity. Molar refraction or refractivity is a measure of total polarizability of a mole of a substance and is dependent on the temperature and index of refraction and the pressure. The index of refraction and the molar refraction are indication of the manner in which a molecule interacts with light. It has many uses as used in confirmation of identity and purity of compound. Molar refraction is also used in calculating surface tension and solubility parameter, which is a measure of intermolecular forces. As we know that the refractive index is affected by changes in temperature, pressure, and wavelength of radiation, but molar refraction remains nearly constant with changes of temperature and pressure by virtue of the density factor, which is function of temperature and pressure. Thus, it is important parameter which must be kept in mind before selection of two or more excipients. Now coming to optical activity, this is also known as optical rotation, which relate to the stereochemistry or chiral carbon atoms. A substance which is optically active is capable of rotating the plane of polarized light. The enantiomers are referred to as plus or minus enantiomers depending upon the direction of the observed rotation. For example, panthenol comes in two enantiomers, D and L. Only D-panthenol is biologically active. However, both forms have moisturizing properties. For cosmetic use, panthenol comes either in D form or as a racemic mixture of D and L form, and thus optical activity play an important role for cosmetic formulations. Adsorption at solid, liquid, and solid gas interfaces. The triple interface found between solid, liquid, and gas will move in response to the forces arising from three interfacial tensions until an equilibrium position is established. Non-spreading liquid gives droplets. Spreading occurs when a liquid of low surface tension is placed on one of high surface tension. If we know the surface tensions of a testings, we can determine the surface tension of a smooth solid surface. When the forces of adhesion are greater than the forces of cohesion, the liquid tends to wet the surface. When the forces of adhesion are less by comparison to those of cohesion, the liquid tends to diffuse the surface. The phenomenon of surface adsorption comes under interfacial phenomena. Knowledge of interfacial phenomena is in cosmetic, and the mechanism by which interfacial properties can be modified by surfactants is essential for proper development of cosmetic products. An interface is a boundary between two of three phases, namely solid, liquid, or gas. Solid liquid, liquid liquid, solid solid, solid gas, and liquid gas. Although an interface is often considered as a plane, it is actually a region at the boundary of phases where various physicochemical properties are different from that of bulk. Chemical species at the interface possess higher free energy than those in the bulk, and this excess free energy, essentially due to the extensive existence of an interface, is known as interfacial energy or surface energy. Actually, there is an increase in the total free energy of the system due to the existence of this interfacial energy, and the increase is proportional to the total area of the interface. A system always tries to reduce its total free energy. The tension that exists at the interface tries to reduce the total surface area, and thereby there is an increase in energy, which is known as interfacial tension or surface tension. Minimization of this interfacial tension is important in the formulation of stable cosmetic, since many cosmetics are emulsion made up of minute droplets of oil in water or water in oil, and hence possess a large interfacial area. A surfactant can absorb at gas-liquid and liquid-liquid interface and reduce the interfacial tension due to the affinity of one part of it to the oil phase and the other part to the water phase. The interfacial tension decreases with addition of surfactant until the CMC is reached. Surfactants can adsorb also at solid-liquid interfaces, and such adsorption can significantly alter the wetting properties. The adsorbed surfactant layer can exist either as a loose gaseous film, liquefied film, or even as a rigid solidified film, depending on the nature of interactions between them. A significant amount of cooperative interaction between the molecules results in rigid films with relatively high interfacial viscosity. Such viscosities are often an essential requirement for cosmetic emulsions. It can help minimize the coalescence between the emulsion droplets, increasing its stability and life. Adsorption of charged species results in charge interface, the nature of magnitude of which will largely determine the extent of attractive and repulsive interactions between interfaces. Allowing a charged interface to form on the emulsion droplets can retard coagulation between emulsion droplets. The charge at the interface is balanced by ions of opposite charge known as counterions, which exist in solution. In general, cosmetics are essentially ensemble of interfacial phenomena critically dependent on the successful application of surfactants. For different applications, the surfactant must possess desirable interfacial properties. Some should have good wetting properties, whereas others should have emulsifying or foaming properties. For example, creams such as suntan creams that are meant to remain on skin for longer intervals have to be formulated in such a way so that they will not penetrate the skin, whereas medical creams will have to be formulated for penetration to the skin. Medical cream or pharmaceutical creams which are used topically for penetration purpose. It is evident that a wide variety of requirements are placed on surfactant for use in cosmetics. With increasing concern for the environment, development of environmentally begin formulation is a current trend. Generally, the cosmetic industry is looking for surfactants that are highly efficient, multifunctional, non-irritating, and biodegradable. Coming to the cosmetic necessities, these are the various agents which are used in order to make a stable cosmetic preparation, like acids, bases, buffers, topical agents, protective and antimicrobials, and astringent. The present slide talks about the use of acids and bases. An acid is a substance which forms H plus ions as the only positive ion in aqueous solution. And base or alkali is a substance which forms hydroxyl ion as the only negative ion in aqueous solution. A base is an insoluble hydroxide, and according to the definition of an acid and a base, an acid is a proton donor, whereas a base is a proton acceptor. Another definition, an acid is an electron acceptor, while base is an electron donor. Now coming to properties of acids, we generally have sour taste, and it should not be tasted as it is corrosive in nature. Acid change blue litmus paper strip to red. Aqueous solutions conduct electricity, so they are electrolytes. They react with bases to form salt and water. Hydrogen gas will evolve upon reactions with an active metal such as alkali metal, alkaline earth metal, zinc, iron, aluminum, forming a salt as the only other product. Evolve carbon dioxide on reacting with metal carbonates. Have bitter taste, and it should not be tasted. It is very harmful. It is very irritant. Feel slippery or soapy. Should not be touched as they react with skin to form soap. Bases turn red. Acidified litmus paper strip back to blue. Aqueous solution conduct electricity. They are electrolytes. React with acids to form salts and water as the only products. Now coming to the properties of bases, a variety of cosmetic includes shampoos and exfoliants use acid-base chemistry in order to improve a person's appearance. Salicylic acid is commonly used exfoliant that is used to treat skin conditions such as acne, psoriasis, and dandruff. The extremely low pH of salicylic acid causes irritation in the skin as skin pH vary from 5.4 to 5.9. This raised pH values helps in prevention of burns and other irritation caused by low pH of the acid. Therefore, every formulation must have appropriate pH so that it could not show any irritation or a reaction at the place of application as such. Properties of bases. Buffering cosmetic chemicals are weak acids or bases which are used to maintain the acidity, that is the pH of a solution, near a chosen value after the addition of another acid or base. Function of a buffering agent is to prevent a rapid change in pH when acids or bases are added to the solution in order to assure the stability of the finished product. There are many buffer systems which are used for cosmetic preparation, like light calcium carbonate, anhydrous sodium citrate, boric acid, diethylamine, glycine, monobasic sodium phosphate, and sodium D-L-lactate. Topical agents, which are medicine topical agents which are generally applied on the area being treated locally, like in creams, ointments, and lotions. There are similarity between agents used in cosmetic and topical therapeutic preparation in some extent. Prime function of cosmetic is to maintain and or improve characteristic of relatively up to normal skin, whereas the function of topical therapeutic agents is generally the cure of abnormal skin. Cosmetic cleansers shows similarity with the cleansers suggested by dermatologists. Both dermatologists and cosmetic chemists suggest the use of non-soap cleansers with water and some without water. Coming to protectives and antimicrobials are used topically for both prophylactic as well as therapeutic purposes. They are included in cosmetic the same way as deodorant and as a means of combating the microorganisms growth in the seborrheic conditions. Antimicrobial agents can be bactericidal or bacteriostatic in their function. The bactericides destroy viable organisms rapidly, whereas bacteriostats prevent their multiplication without direct killing. Nowadays, alcohols and antibiotics are bactericidal agents most frequently used in cosmetic and other topical pharmaceutical preparations. Protective and antimicrobials, antibiotics are incorporated into ointments and lotions, bacteriostatic agents into ointments, lotion, and cleansing preparations. For prophylactic purpose, surgeons and dermatologists have found topical antimicrobial agents which are quite satisfactory, but on the other hand, these agents are less satisfactory for cutaneous disorders. Protective and antimicrobials are used for prevention of microbial growth in cosmetic preparations, which gives stable formulation during storage. It should be added to maintain their identity as well as their homogeneity. Astringents, they are also referred to as toners, and they are chemical compounds that contract the tissues. And astringents are used to tone the skin and make it firm by constricting the pores. Now, this constriction is due to the precipitation of proteins, and these astringents create a protective layer between the underlying layer of the skin with the external elements. They are said to contain antioxidants that fight bacteria on the skin and help it to look clean and fresh. Green tea is a natural astringent that is widely used. The astringents are the stronger form of toner, contain a high proportion of alcohol, which varies from 20 to 60% sometimes, and antiseptic ingredients, water, and humectants. Now, coming to chemistry of emulsion in cosmetic formulation, the majority of creams and lotion used in cosmetics are emulsions. An emulsion can be defined simply as two immiscible fluid in which one liquid is dispersed as fine droplet in the other. Homogenized milk is an example of a typical oil in water emulsion. Milk fat, which is the oil, is dispersed in water as fine droplets by the homogenation process. The reason the fat does not flow to the top immediately is due to the presence of emulsifier, and in this case a milk protein called sodium cyacinate as well as several phospholipids. The reason for popularity of emulsions are that it allows incorporation of both polar and non-polar material in the same formulation. Traditionally, emulsion technology has been associated with skincare products, but now the application of emulsion has become much wider. Emulsifiers greatly determines the degree of continuous residual film on the skin surface. Hair conditioner, antiperspirant, color cosmetics, and cleansing products today have taken advantage of latest emulsion technology. The fundamental basis for emulsion technology is the interactions among water, surfactant, and oil. Now coming to importance of branch chain compounds in cosmetic products for care of human skin consist of a base which incorporates the special reagent chosen for specific use. And this cosmetic base should not only be carrier for the active material but should themselves also exert the greatest possible positive effect on the skin. The creams and lotions commonly used in cosmetics are emulsions of hydrocarbons, fats, natural or synthetic waxes, emulsifiers, and water. Natural fats used in large amount are often triglycerides of straight chain fatty acid, for example, stearic and palmitic acid, and such high molecular triglycerides hinder the passage of water vapor from the skin, and the branch chain analogues have clearly better properties. Various branch chain compounds were developed for the cosmetic industry, like hydrocarbons, carbonic acid, alcohols, and ester, which are used for raising of spreadability of the cosmetics. Occlusivity is important parameter of cosmetics. It is degree to which passage of water to and from the skin is controlled. Products for hot humid conditions where water loss from the skin is important need use of branch in excipients which allow evaporating the moisture from the skin. Preparation having branch chain esters bases showed a good spreadability with non-occlusive effect. Small quantity of branch chain compound is good enough to show their effects than straight chain compound. Now coming to summarization, let us now summarize what we have learned in this module. We have talked about surface tension and viscosity, particularly with respect of cosmetic products. We have seen the difference of amorphous and crystalline solids and what are polymorphic form and the associated physical properties and the importance of acids, bases, buffers, topical agents, protectives, antimicrobials, and astringent in cosmetic preparation. And then we have also talked about the chemistry of emulsion formation in cosmetics. Thank you.